semi-classical analysis, what happens if we go and look at the full quantum dynamics? So we're interested in this regime where we have a single photon excitation, and I want to look at a parameter space where this single photon excitation pushes my mechanical oscillator by a lot. And in terms of the constants in my Hamiltonian, this is the regime where the coupling strength squared is larger than the cavity decay rate times the mechanical frequency. I want this term to be greater than or equal to 1. Okay. And in this regime, the discreteness of these photons comes important, so the fact that they come in chunks will play a role. And a single photon into my cavity pushes my mechanical degree of freedom by more than its 0-point line width. So the photons really push this mechanical degree of freedom. So the most basic trick that one can do to solve for the dynamics is to go to a what's called master equation. Okay, master equation is just an equation for the density matrix of a quantum system that takes into account the fact that you can lose energy to an environment. Okay. So this is the equation to find a steady state solution for an optomechanical problem. It has the usual evolution from the von Neumann equation, and then you have these script L's, which are called Liouvillean superoperators, and these are operators that describe dissipation. Okay, and here I've written them out in their full detail for those who know what these are. The important part is these describe the dissipation or the loss of energy from my system into the environment. Now the next thing before we get to the results is we want to quantify what it means to have a nonlinear state of my mechanical degree of freedom. I told you the Wigner function is useful for this because it will have negative regions. And so the idea is we're going to chop up our Wigner function into little pieces. We're going to do this numerically. Okay? And then we're just going to count the number of negative pieces. Here the negative pieces are in red. So we add up all the negative regions and we're going to weight each of them by the value of the Wigner function at that point. And then we're also going to add up all the positive ones, and we're going to take the ratio of the negative terms, the absolute value divided by the positive terms. Okay. And this is what we'll call eta, and this is this non-classical ratio. Okay. So this will describe how non-classical a state of my mechanical oscillator is. So let's look at some results. So in general, you can't describe in closed form the solution to this particular system. So I've just done a numerical simulation of this system. So let's see what we get. So here on this top panel, what I've done is I've varied this laser frequency, this detuning, and I've also varied the coupling strength G0. So this is my parameter space. So this first panel here, this tells me the number of excitations in my mechanical degree of freedom. Okay. So there's a few things to note. First, this term here, where the detuning is 0, this is when I'm driving my laser on resonance. Okay, and you'll see there's just a few phonons in my mechanical degree of freedom, something about 40. But then remember I told you that there are also things like mechanical sidebands, so n times omega m. Here we have the first sideband, here we have the second sideband, and here we have the third. So you can see we have these places where you have a large number of phonons inside my mechanical degree of freedom, and you can see that each of these lines takes a left-hand turn. This left-hand turn is this frequency pooling that I talked about earlier. Remember, you have the Lorentzian peaks, and they started bending to the left. These curves are bending to the left because of this nonlinearity. Okay. And to show that, I've just plotted the line, dashed line over the top that shows this is indeed the case. This second picture here, this is the actual values for this non-classical parameter eta. All right. So regions that are not black in this plot are regions where my mechanical degree of freedom is in a quantum state, and the closer to white, the stronger the quantum state. So we can see that the strongest quantum states are when my detuning is near 0, you get very, very strong quantum states. Okay, and then as I go to these mechanical sidebands, I also have non-classical states, but they get weaker and weaker. All right, strongest here, and then weaker and weaker and weaker. Okay. Another thing to note is if I fix, for example, my detuning to be 0, and I increase my coupling strength, then I go from no quantum to very, very large quantum states, and then if I just keep going, it goes back to 0. So we'd like to explain all these features. So the last thing is this Fano factor, this F function. Okay, and here it's plotted on a log scale. So if the function here is 0, that means the Fano factor is 1. So anything that's white is essentially a coherent state. Anything that's in red is a sub-Poissonian state, and anything that's blue is a what's called a super-Poissonian state with F greater than 1. So remember I told you that if F is less than 1, we have quantum states. And in general, we do get some quantum features in the regions where this function has F less than 1, but you see, for example, here at the strongest quantum state, this is around 1.3, it doesn't actually occur where the Fano factor is less than 1, it actually occurs where the Fano factor is around 5. Okay, so this seems to contrast what I stated earlier. And we'd like to explain why you get strong quantum states where the Fano factor is greater than 1. Okay, that makes no sense. Right, so what's going on? Oh, sorry. There. So what we're going to do is we're going to look at 2 points. I'm going to look at the strongest point, the strongest non-classical region, which is going to be the green star, and then I'm going to pick another point that I just kind of randomly picked, which is this blue star up here. I want to see what's going on. So here is the strongest quantum state. This is the green star. And what I've done is on the left here, I've plotted this Wigner function, this probability distribution. And you can see it has a bunch of negative rings. Right? This signals that indeed the state is quantum mechanical. Okay, and unfortunately we can't see it, but barely there's another ring on the outside here. And what I can do is, in order to understand this even better, is I can take this and I look at the number state distribution of the mechanical oscillator. And what I find is something interesting. I find that the mechanical degree of freedom actually has 2 different vibrational amplitudes. Has 2 different limit cycles. I have a big peak here around n equals, let's say, 10, and I have another one here that's around n equals 42. So I told you in the semi-classical analysis you could have multiple oscillation amplitudes, okay? And these dashed lines here and here, these are the semi-classical oscillation amplitudes that one would expect. So what's going on is that most of the time my mechanical oscillator is vibrating with a number of quanta around 10. Sometimes it actually will switch to a higher amplitude state with n equals around 42. So I have 2 different limit cycles here and here, and if I calculated the Fano factor for this particular state, I asked what is the variance of this distribution. Because I have 2 peaks separated by a large distance, this variance is going to be huge. Okay, and I get a Fano factor of 5.2. I can go to the other state, which is this blue star. I can look at the exact same thing. Here is the Wigner function. Okay, again, it's circular. You see you have regions of negativity, and then you have a bunch of rings. Okay. In this particular case, at this larger coupling, my mechanical oscillator is not vibrating at 2 different amplitudes. It's vibrating at 4. So I have 1, 2, 3, and 4. And again, these dashed lines are what you would get from the semi-classical analysis. So again, this is a quantum state, but its Fano factor is going to be larger than 1 because if I look at this variance, it's going to be huge, and it's around 10. Okay. So these large variances come from the fact I have multiple oscillation amplitudes. And the general idea is the stronger the coupling, and also the more excitations you have in your oscillator, the more of these peaks you'll see. So you always have a large Fano factor. The reason it turns out these states are still quantum mechanical is if I look at each of these pieces individually, both of them are sub-Poissonian, provided I look at each of them individually. And I'll return to that in just a couple of slides. So I want to now understand why, if I, for example, fix the detuning at delta equals 0, and I increase the coupling, I want to understand why I go from classical to quantum states to somehow classical states again. Why does this happen? So what we're going to do is we're going to fix the detuning and sweep the coupling strength from 0 to 3. And I'm going to use a special tool to look at this, and I'm going to use the number state corresponding to the maximum probability amplitude in my density matrix as essentially an effective order parameter. So what these black squares I'm going to tell you about in just a sec, these represent which phonon number my oscillator is most likely to be vibrating with. So I want to connect this back to the micromaser. So in the micromaser, the key was this maser pump parameter. Okay? And in our optomechanical system, the coupling strength divided by kappa is the exact same thing as this micromaser pump parameter. Okay? In this case, the interaction time is given by 1 over the cavity decay rate. So this decay rate measures how much time or the inverse of how much time it takes before my photons are leaked into the environment. So here I've plotted two different pictures. This is the standard micromaser. This black line here is their version of this order parameter. So it starts near 0 and then rapidly rises. This represents something like a threshold in standard laser physics, and then it eventually reaches maximum, comes back down, and undergoes these oscillations. Here, the dashed line is a Fano factor, or this is called a Q parameter, but it means the same thing. You see that it goes from a low value, peaks to a high value before the order parameter maximizes, goes down, and oscillates back up. This is the characteristic feature of a micromaser, and this is what makes it different than a standard laser. Okay, this does not occur in a normal laser. So I want to plot the exact same thing, okay, but instead of looking at the electromagnetic cavity of a micromaser, this is now my mechanical degree of freedom. So I'm looking at phonon numbers. And so what we see is if you look at the black squares of the order parameter, you see that they do a very similar thing. You start near 0, which means my mechanical oscillator is not vibrating at all. At some critical value of the coupling strength, the coupling now overcomes the dissipation, and I get a sharp rise in my phonon number. So this is a laser threshold, also called the micromaser threshold. So my system starts to vibrate very, very strong, and then starts to drop back down. At some point, something interesting happens. I get a jump. Okay. So there's some value where this effective order parameter jumps. This jump characterizes now that a different limit cycle is now the most probable state of my system. Okay. And you can also see as a similar thing for this Fano factor here, my dashed line also does a similar kind of behavior. Okay. And this shaded region, this tells you where the mechanical degree of freedom has the most non-classical states. It's in this region. Okay, but you can see that these patterns are essentially identical. And this kind of confirms the idea that this system does the same dynamics.
Excuse me. What is the frequency difference between the mechanical, your mirror frequency, oscillation frequency, and the photon frequency?
Oh, the photon frequency is in practice much higher.
Oh, okay.
So usually the mechanical degree of freedoms are usually something about, at least for systems I'll deal with, are around 10 megahertz, and your optical cavity can be even gigahertz. There's usually a very large nuisance.
So you don't have this parametric instability.
So there is, you can think of this rise in oscillation amplitude as kind of an instability. So you can think of it that way, so I don't want to say no, but it's related.
No, but parametric instability is when these two frequencies are close.
Oh yeah, no, they're completely separate. That's your definition.
So
Yeah. At least in practice, so in theory, that's what I do. All right. So we see we get a jump to a different limit cycle, and then as we jump to this different limit cycle, we can see that the region where these states are quantum essentially vanishes. So let's see why that is. All right, so why do quantum features disappear at higher couplings? So here what I've done is I've taken the exact same plot I showed you, but now I plot the distributions in the number state basis for these states. Right, so here's the coupling strength. I start at 0.5, and this is the number state. So if I start at 0.5, I have one particular limit cycle, and its distribution is given in red. Okay. And this distribution is going to be a large distribution. So here in blue, I have the distribution for a coherent state. So this corresponds to f equals 1. So this large distribution will have f larger than 1. But as I turn on the coupling strength, this red distribution is now narrower than the blue coherent state. And so this signifies a Fano factor that's less than 1. Okay. And as I keep going, you see it gets squeezed more and more, but eventually you notice another bump pops up. And this is another vibrational amplitude. So here, this is this little peak I showed you earlier in the most quantum state. It just begins to pop up, and if I keep increasing the coupling strength, these two peaks get larger and larger, and then they begin to merge. Okay. And this merger happens in this case around the coupling strength of 1.3. And if we look here, this is kind of just a line plot of the same thing. So here what I've done is I've plotted the Fano factors for this red limit cycle and this smaller green limit cycle. Here's the red and here's the green. So the green starts around 1.2. Okay, and you can see that as long as my coupling strength is on the order of about 1 or so, both of these individual limit cycles are sub-Poissonian. F is less than 1. All right, so both of these limit cycles are in non-classical states, right, which is why my Wigner function is negative. But at some point, and it's again where these two limit cycles start to merge, which is around 1.3 here, then if I look at this non-classical parameter eta, it goes from a maximum value and starts to drop. This is this dashed purple line here. So why does it drop? So it turns out that if these two limit cycles are separated enough in this number state basis, I can consider them separately. Okay, so they're very far apart, they don't interact. And I can consider each one as a separate distribution. Okay. But when, as I crank up the coupling strength, these limit cycles begin to merge, okay, I can't partition them into two separate limit cycles. I have to consider now the full distribution of my oscillator, and as we've seen, this full distribution has a Fano factor that's very, very large. Okay. And so once these two limit cycles start to interact, this full distribution now plays a role, and because it has an F factor larger than 1, this non-classical parameter drops. So the overall resonator distribution, which is super Poissonian, F much, much greater than 1, determines the non-classical properties, and those states really are not very quantum at all. And in general, this overlap occurs where you have more and more phonons in your mechanical resonator, and this is why if you go to higher and higher mechanical sidebands, that you get less and less quantum features, because you have too many phonons in your system. So you get smaller quantum features at the mechanical side. Okay, so let's summarize what we've learned. So you can actually generate non-classical states of a mechanical resonator in an analog of this micromaser, provided you sufficiently damp your optical cavity mode to have at least, or sorry, at most, one photon at any given time. You get sub-Poissonian limit cycles. You get non-classical Wigner functions, which are negative. And you also get phonon oscillations that are the characteristic signature of this micromaser. Now, this particular system I told you about, this is actually the first micromaser system that actually doesn't have an atom. Just harmonic oscillators. So this is the first single atom laser with no atom, which kind of sounds fun. But the general idea is this helps to understand the generation of quantum states in these macroscopic mechanical systems, and then we can use this now as a tool to understand this quantum to classical transition, because everything I've told you, this same Hamiltonian applies to over 20 orders of magnitude of mass. Right? So there, in principle, there's no limit to what size oscillator you could put in. So I have one slide left, and the question now is, this is all theoretical, can we build the thing? Right? And if you asked me this a year ago, the answer would have been no, because this is a very hard thing to do, but actually the answer is yes. And the thing we use is what's called a cavity Cooper pair transistor. So this is a superconducting circuit device. The most difficult part in building something like this is this single photon strong coupling. So again, the coupling strength divided by the decay rate and the mechanical frequency has to be larger, or at least on the order of 1. Okay? And no one could even come close to this. So here I put a few systems that have already been published that look at optomechanical systems. So for example, a superconducting circuit. Again, the key parameter is this guy here. I want it to be on the order of 1. I have 10 to the minus 7. Optomechanical crystals, you get something on, again, on the order of 10 to the minus 6, 10 to the minus 7. For atomic gases, because the gases, they're made out of atoms, you can actually do quite good. This number is actually 7,500. So this is a very good number, but the problem with these atomic gases is they're not very large systems. You only have about 10 to the 4 atoms in these atomic clouds. Okay? And we want to get something bigger. So the thing that myself and collaborators at Dartmouth College proposed is to use a superconducting circuit device, and I'll explain just briefly what it does. And in principle, you can plug in the numbers, and you get a factor of 14 in this device for about 10 to the 9 or 10 to the 10 atoms. So this is roughly the same number of atoms as in a piece of DNA. Okay. So this number here is 7 orders of magnitude larger than what people have been able to do. Okay, so this is why we're extremely happy about this, is because this device in principle should be very, very good. So the idea is you use what's called a Cooper pair transistor, which is formed by 2 superconducting Josephson devices, and you put it inside a microwave cavity. And then what happens is, if you take a mechanical degree of freedom and you couple it capacitively to the center island of these 2 Josephson junctions, then as the mechanical oscillator moves, it changes the charging energy for electrons on this island, and then the current that flows from the center line into the ground plane is modulated by this motion. Okay, so this modulates the charging energy, and what this does is this in turn causes a measurable frequency shift of this superconducting cavity. So I can actually measure what's going on in this mechanical degree of freedom with this microwave cavity. Okay, this is the only system that we know of where you have large numbers of atoms and you can reach this strong coupling regime. Okay, so in principle we can build it, and people are working on this right now. Okay, so with that, I'll end. So thank you very much.
Questions?
So 2 questions. I'd like to first one is that I'd like to clarify that if the Fano factor is larger than 1, is that a classical? Is that a quantum?
That is classical.
Classical?
Mm-hmm.
I thought it's a coherent state is equal to 1.
Equal
that's
to 1.
Class 1. I mean, if it's larger than 1.
So those are classical states. Those are, again,
Superposition.
Yeah, super-Poissonian states are classical states. Sub-Poissonian are quantum states.
Okay, so the second question is that what if your coupling is linear?
Well, if you have a linear coupling between two oscillators, you can never put a mechanic or any oscillator into a quantum state. It would always be coherent states because the coupling is linear. So you need a nonlinear coupling. Linear coupling only gives Gaussian states, which are coherent states.
But you also have a pump field, right?
To drive, you need some input energy source. Yeah. So I'm driving the electromagnetic cavity. Got to put photons into my system. That's linearly coupled. But the coupling between the photons in the mirrors and the mirror coupling, that radiation pressure coupling, that's nonlinear. If you want to think about it, it's the number operator squared, which is nonlinear.
You have this super-Poissonian distribution for classical state, and I presume this is related to photon bunching.
Yeah, you're looking at this.
Yeah, right. And but I think would this characteristic of whether the distribution function is Poissonian or super-Poissonian or sub-Poissonian not be a good definition for quantum state or classical state? I mean, okay, let me put the question another way. If you have a bunch of thermal photon, which is classical, and you will have a photon bunching, and what would this photon distribution would look like? Would it be looking like? Would it look like what you present for this classical? I mean, different your final figure on the top. Will it make a transition to classical?
I don't think so, but obviously, not doing it, I wouldn't know, but I would suspect not.
Right. So it's apparent. I mean, by looking at the distribution function, they are quite different, and so I would suggest that maybe it's by looking at by using this Fano number, maybe it's not a good characterization of whether it's classical or quantum.
I mean, in some sense, you're right, which is why, as kind of the ultimate verifier of a quantum state, I use negativity of the Wigner function. So yeah, the Fano factor can be less than 1, which would be sub-Poissonian, which is usually characterized as being quantum. But then your Wigner function would still be positive. And so, to me at least, the way I usually say a state is, a quantum state is by negativity of the Wigner function. That's why I use this, because there's no question about that. But yeah, the Fano factor, you can run into things that are a little more subtle, right? But for these things, that's why we use the negativity of the Wigner function.
Yeah, I have a question on this gamma you introduced.
Yeah.
It's a dissipation.
Yes.
So but your simulation didn't show any gamma effect.
Yeah.
Because, because gamma is important for the loss of information, coherent information.
It is.
The phase information.
It definitely is.
If it's gamma is very huge.
It is.
Your system is just going to classical.
So as in order to save time, I erased that slide because I didn't think people would care.
Oh.
And so you apparently care.
Yeah.
So in order to see any of these effects, the quality factor of the mechanical degree of freedom has to be quite large. And in this case, it was 10 to the 4, which is large depending on who you talk to.
Yeah.
So yeah, definitely. And if you add a non-zero thermal environment, then this state being analogous to the micromaser, what you find is that even a really weak thermal environment really kills the quantum features of the states. So it's in the paper, and I had a slide, but then I removed